Hi everyone, this is Mr. Lee. In this video, we are going to go over energy and capacitors. All right, let's begin. So if you remember in class, we did a very quick demo where we charged up a capacitor and we also connected a light bulb to the capacitor and we saw what happened. So just as a quick reminder, I'm going to just sketch out the scenario. So we had a EMF source or a battery, and we made that battery connect to a capacitor, and we also had it connect to a light bulb. And then we had, I'm just going to call it a switch. The switch was just me manually connecting the circuit together. So there's a couple of very important things that happened when this circuit was allowed to run. The first one, I'm going to call t equals 0 seconds. So this is as soon as the connections have been made, the light bulb lit up, right? And it was very, very bright, very bright. But then as time it continued, we saw that the bulb got dimmer, but it was still lit. Okay, and we also saw that as time got very, very long, the bulb went out. All right. So the important part about this demo was that we saw that as soon as the circuit was complete, that there was a flow of charge, and that flow of charge allowed for the capacitor to start building up charge. And so, if we were to do a quick little note on the side here, we would say charges were added with no resistance. So in the beginning, all the charges were added to the capacitor with no resistance, but then as time went on, adding charges became difficult. Okay, and we also discussed why this was the case. And so the reason why adding more and more charges becomes more and more difficult is because each side of this plates of these capacitor plates has a certain charge. The left-hand side, which is connected to the longer side of the EMF, will be positive, and the side that's connected to the shorter end of the EMF will be negative. And so we discussed that the negative charges were constantly being stored on the negative side. And as we were adding more and more negative charges to that side of the plate, due to Coulomb's law and just the nature of charges in general, the charges would start to repel the addition of additional charges. So we're going to go into that idea right there, okay, of why it was so hard to add new charges. All right. Now, I'm going to phrase this very carefully because in this phrase here is the conceptual knowledge that you'll need for the energy of a capacitor. So with this demo, we were able to make the following claim. So as more charges were added, okay, we required more force. Okay, I'm gonna put force in quotes because we know it was Coulomb's law, right? We require more force to add more charges. Now, the reason why I want to make sure that we understand that we were adding charges and that addition of charges required work is because when you are pushing a object using a force over a certain distance, that is the word work. Okay, so this is the definition of work. And if you remember from the mechanics unit, work is the change in energy. And for our case here, this will be the change in electrical potential energy. And right there is the start of our formula. All right, so I'm going to do a quick little underline there with a quick little statement. So it's important to know that the work that we are doing, so the work is done on the charge. Okay, so we are doing work on the charge, but it's very important that we know the potential energy is stored in the field. Okay, in this case, will be electric field. This is a concept that was discussed earlier in the electrostatics unit, where energy is stored. So gravitational potential energy, the energy stored in the gravitational field. Electrical potential energy is stored in the electric field. And that the importance of that will come up. Okay. So if we were to take a look at the highlighted portion as to why this is so important, we can take a look at a quick sketch of a capacitor, right? So if we have a EMF source, right, and we have a capacitor like so, we know that this side will become positive and this side will become negative. So in the beginning, there are not a lot of charges, so the field is pretty weak. Okay, so less charges, smaller E field. And this kind of makes sense because there's not enough charge there to produce a big amount of field, so it's pretty small. So using this idea, we can reword this, and so if we say there is a smaller E field, that means there is less potential energy. And this should also make sense, right? The more we charge a capacitor, the bigger the potential energy is stored in the capacitor, right? And so as we add more Q, or in this case, as we charge up the capacitor, the E also increases. And so as we add more Q, not only does the E field increase, but the electric potential energy also increases. So it'll look, right, it'll look a lot stronger and a lot more dense. So the red here is showing you the change or the addition of more charges. All right, so with all that out of the way, let's actually get into the formula of it. So that's the conceptual ideas. Now let's try to apply some formulas. So the first thing is let's come up with the conservation of energy formula and the work energy theorem. So we know that work is equal to the change in potential energy. And for our case here, it'll be the change in electrical potential energy. And we already defined this in the previous unit. We know that this is Q delta V. Okay, but from there, what we want to look at, because we are a calculus-based course, is as we are adding a tiny bit of charge, right? So as we are adding or as we're moving a tiny bit of charge, so that will be a change in the work, right? We are changing the potential energy, or excuse me, the electric potential energy of the capacitor. And we want to see how we can do this using the powers of calculus. So before I write the rest of this equation here, I want to quickly define something. Instead of writing delta V or dV on the other side, I'm going to use a different notation. I'm going to write V prime. And for here, V prime is the delta V at any instance. Okay. Yeah. So what we get here will be a change of, right, as we are adding tiny bits of charge, we will get a addition of the delta V, right? The more charge we add, the greater the potential becomes. Yeah, so from there, we can do a integration, and our integration becomes, so we're going to integrate both sides, and we end up with the electric potential energy is equal to the upper bound will be the total amount of charge on the capacitor, starting from zero amount of charge to the total amount of charge, and then we get V prime dQ. All right, so at this moment, what I want to do is I want to, over here on the right-hand side, give you a chance to write down a couple of formulas that we need to move on. So one of the things that we need to do is we need to use the capacitor formula. So we know that capacitor, or capacitance, excuse me, is the total charge over the change in the voltage. So if I rearrange the formula, we will get delta V is equal to the total charge over the capacitance. But if we want to use this formula for what we need, we would rewrite this as V prime is equal to Q over C. okay, where that Q isn't a tiny amount of charge that we're adding, but the total amount of charge that we have added to the capacitor. And the reason why we want to do this is because I want to substitute in that formula into what we just had over here. That way we can actually integrate with respect to Q. So if I substitute that in, we would get from 0 to Q, we will get Q over C dq. And at this point, it's just calculus. And so let's go through the calculus together. The integral, or the constant that we can pull out, is the C, and the integral of q dq will be 1/2 q squared. So we have 1/2 q squared divided by c, with our limits of 0 to q. And that's all equal to electric potential energy. And we substitute in our bounds, and we would get capital Q squared over 2c. And this is one of the formulas that we get on for our electric potential energy for a capacitor. However, you won't find this formula on the equation sheet for your the AP formula sheet. So I'm going to show you how we can get those two. All right, so the first thing that we want to do is we actually want to go back to this formula right here. Okay, I highlighted that in purple. I'm going to rewrite that down here so that we have that as a reference. So we have C is equal to Q over delta V. On the formula sheet, I believe there are two different forms of the equation, so I'm going to show you how we can get both. So for the first one, I want to substitute in my my capacitance. Okay, so we get UE is equal to Q squared over 2, and I'm going to put my substitution in my as a parenthesis so you can see exactly what I'm doing. Q over delta V, like so. Okay, so we get Q squared over 2Q delta V, and with the powers of algebra, what we end up with is 1/2 Q delta V. And this is one of the formulas that you'll see. So this is the electric potential energy for a capacitor. And the other one is we're going to substitute in the Q. So the Q that we're going to substitute in is C delta V. Now, if you know anything about me, you know that I like to show all my steps just so that I don't get anything wrong. So instead of writing C delta V squared, because it is squared, I'm going to just show that there's two of them, C delta V times C delta V. Okay, so that's my Q squared substitution all over 2C. Right. And so here we can see that one of the C's cancels out with the denominator C, and we end up with C delta V squared all over 2. And this is the other formula that you'll see on your formula sheet. So that is how we can derive the two formulas from your formula sheet. All right. So just a couple of quick updates. We have to know that the electric potential energy in the capacitor, okay, we say it is stored in the electric field, and the electric field is generated because we create, as we add more and more charge, the electric field grows, and we are forcing the electric charges to go on the plate, because remember, like charges don't want to be next to each other, and that is how the electric potential energy increases as you charge up a capacitor. All right, this next part of the video, we're going to go over what we call the energy density in a field. Okay, so this is one of those relationships that you should know how to look for, or what to look for. So let's start off with the capacitor formula, where capacitance is equal to epsilon naught, which is the vacuum permittivity, A, which is the surface area, divided by D, which is the distance between the two plates. And because our between the two plates there's an E field that is created, we're also going to show the E field formula like so. All right, so we have these two formulas, and with these two formulas, let's come up with this idea called a energy density field. All right, so I'm going to start off with my electric potential energy formula for a capacitor that we found before. C delta V, and this delta V is squared divided by 2. I'm going to substitute in for my C here. I'm going to highlight right there. And that delta V, I'm going to substitute in. Let's do it here. This delta V will be in for there. Okay. All right, so we end up with epsilon naught A over D. This is my C. So again, I like showing where my substitutes come in. So I'm going to use that highlighter function. And we get E delta X, but that is squared. So I'm going to put 2 of those in there. E delta X all over 2. All right, so let's clean this up a little bit. So we get E epsilon naught A over D. And then here we have E squared. And then we have delta X squared. But I just wanted to point out that this separation between the two plates and this delta X, these are the same thing. Okay? And so instead of writing delta X squared, I'm just going to write D squared. And the reason being, it makes our math a lot cleaner. So we see one of the D's in the denominator cancels out with one of the D's in the numerator. And our final formula that we end up with is a half of this epsilon naught A E squared is equal to the potential energy for the capacitor. Okay. I forgot a D there. All right. Now, if you're taking beautiful colored notes at home, I want to highlight the A and the D. So the area times the distance between them, A times D, this is just the volume. Okay? And the reason I want to point that out is because if I divide A times D from both sides, we get UE divided by A times D. So this is energy per volume. So this is how much energy is in our field per the volume of the field, because electric field takes up space, and we will get 1/2 epsilon naught E squared. Now it's important to know that this 1/2 epsilon naught, that right there, this is just a constant, so I don't want us to pay too much attention to it, but rather I want us to pay attention to this idea of this energy volume with this E field. We see that the potential energy volume, right, has a square proportion to the energy or the E field. So let's say if we triple the strength of the E field, that means the amount of energy that we are increasing by increases by 9 times. Okay, it's not a directly proportional relationship, rather a square relationship. All right, wonderful. This is the first part of the energy in a capacitor. I'll see you next time where we go over some conceptual ideas behind energy and capacitors and doing work with a dielectric. All right, I'll see you next time. Bye-bye.